You're falling toward a neutron star, an object so dense that a teaspoon of it weighs 10 million tons, more than Mount Everest. Before you even get close, gravity starts tearing you apart, atom by atom. This is what happens in the final seconds, before you hit the surface. And trust me, you don't make it there intact. A neutron star is what remains after a massive star explodes in a supernova. When a star 10 to 25 times heavier than our Sun runs out of fuel, its core collapses. In less than a second, all that mass compresses into a sphere only 20 kilometers across. That's roughly the size of a city, Manhattan, crushed into something you could drive across in 15 minutes. The density is almost impossible to imagine. 1 cubic centimeter weighs 400 million tons. All the cars on Earth could fit in a space the size of a grain of sand. Protons and electrons are squeezed together so tightly, they merge into neutrons. Hence the name. The gravity at the surface is 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you'd weigh as much as Mount Everest weighs on Earth. Your body would be flattened to less than the width of an atom. Let's say you start 1,000 kilometers away. You're already in serious trouble. The gravitational field here is 100,000 times stronger than Earth's. You begin to accelerate, fast. Within the first second, you're falling at 1,400 meters per second. After 2 seconds, 2,800. By the time you've fallen 100 kilometers, you're traveling at nearly 5% the speed of light. But speed isn't your main problem. It's tidal forces. The gravity on your feet is stronger than the gravity on your head. Your body begins to stretch painfully. At this distance, the force is already 1,000 times your body weight. Your spine stretches, bones crack, NASA's models show your skeleton would fail within seconds. No human body can survive forces this extreme. At 100 kilometers from the surface, you're experiencing what physicists call spaghettification. The technical term is tidal disruption, but spaghettification is more accurate. The gravity at your feet is now millions of times stronger than at your head. Your body stretches vertically. Your arms and legs pull away from your torso. Blood vessels rupture. Organs tear apart. You're being transformed from a three-dimensional human into a thin stream of atoms. At the same time, you're being compressed horizontally. The neutron star's gravity doesn't just pull you down, it pulls you inward from all sides. Your width shrinks. Your body becomes narrower and longer, like a rope being pulled tight. Dr. Neil deGrasse Tyson described this process in his book, Death by Black Hole. Though he was discussing black holes, the physics near neutron stars is similar. Quote, "Your body would be stretched into a thin ribbon of matter, one atom wide. That process begins here, 100 kilometers out. If somehow your atoms are still connected, you now face a different problem. Radiation. Neutron stars emit intense X-rays and gamma rays. At 10 kilometers distance, you're inside the magnetosphere. Neutron stars have the strongest magnetic fields in the universe, about 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have fields 1,000 times stronger than that. These magnetic fields accelerate charged particles to near light speed. When these particles hit your atoms, they release X-rays. The radiation dose at this distance is approximately 100,000 sieverts per second. For reference, 5 sieverts is lethal to humans. You're receiving 20,000 times the lethal dose every second. But radiation is the least of your concerns. The tidal forces have already shredded you into component atoms. Your atoms are now ionized, electrons stripped away by the intense radiation. What remains are bare nuclei. You're no longer matter in any recognizable form. You're plasma. 1 kilometer from the surface, you're traveling at 40% the speed of light. That's 120,000 kilometers per second. Time dilation effects become significant. From your perspective, time flows normally. But to an outside observer, watching from a safe distance, you appear to be moving in slow motion. The stream of plasma that used to be you is now experiencing gravity, 100 billion times Earth's. The tidal forces are so extreme, that even individual atoms are being stretched. Atomic nuclei elongate. The electron clouds, if any electrons remained, distort into elliptical shapes. The temperature here exceeds 1 million degrees Celsius. Friction from particles in the magnetosphere heats everything to extreme temperatures. Any molecular bonds that somehow survived this far are now broken. You exist only as individual nuclei and free electrons. Research published in the Astrophysical journal in 2018 modeled matter falling onto neutron stars. The simulations showed that all complex structures break down within the final kilometer. Atoms, molecules, even the structure of atomic nuclei begins to fail. You hit the surface at 150,000 kilometers per second, half the speed of light. The kinetic energy is staggering. The surface of a neutron star is solid. It's called the crust. It's made of iron nuclei, arranged in a crystalline lattice. This material is 10 billion times stronger than steel, but when you hit it at half-light speed, even this impossibly strong material reacts. The impact releases energy, equivalent to multiple nuclear bombs. Your constituent atoms smash into the iron lattice. Nuclear reactions occur, fusion, fission, particles created and annihilated in femtoseconds. A burst of gamma rays erupts from the impact site. The iron crust absorbs your mass. The 70 kilograms of atoms that were once you are now part of the neutron star. They settle into the crystalline structure, crushed by gravity, into a layer less than a millimeter thick, spread across several square meters of surface. NASA's Neutron Star Interior Composition Explorer, launched in 2017, studies exactly these surface impacts. Material falling onto neutron stars creates detectable X-ray bursts. These bursts help scientists understand the composition and behavior of matter under extreme conditions. After impact, nothing recognizable remains. The atoms that composed your body are now part of a neutron star's crust, compressed to nuclear density. Each of your atoms is now pressed against trillions of others in a space smaller than a pinhead. Below the crust, conditions become even more extreme. At depths of about 1 kilometer, the pressure is so intense that atomic nuclei merge into a neutron fluid. Individual protons and neutrons lose their identity. They form a superfluid, a liquid that flows without friction. Even deeper, at the core, matter may exist in forms we've never observed. Quark matter, strange matter, states of matter that can't exist anywhere else in the universe, except in neutron star cores and particle accelerators. Your atoms will remain there for billions of years. Neutron stars cool extremely slowly. They'll outlive most other stars. Long after our sun dies, the neutron star will still exist. And somewhere in its crust, a microscopic layer of iron nuclei that were once you. Could any technology protect you? The short answer is no. The strongest materials we can create would fail instantly. Carbon nanotubes, the strongest material known, have a tensile strength of about 100 gigapascals. At 100 kilometers from a neutron star, the tidal forces exceed 1,000 gigapascals. Your protective shell would be ripped apart like tissue paper. What about a force field? Some theoretical propulsion systems propose using magnetic or gravitational fields as shields, but the neutron star's magnetic field is trillions of times stronger. It would overwhelm any human-made field immediately. The only way to observe a neutron star safely is from a distance, at least 1,000 kilometers away, preferably farther. Beyond that point, specialized spacecraft could theoretically survive, but no human could. Falling into a neutron star is one of the most violent deaths physics allows. You don't die from suffocation or cold or radiation. You die from being torn apart by gravity itself. The process takes less than 1 second, from 1,000 kilometers out, spaghettification at 100, complete atomic dissociation at 10, impact at half the speed of light at the surface. And finally, compression into a layer of iron nuclei 1 millimeter thick. Neutron stars are the universe's ultimate demonstration of gravity's power. They take matter and compress it beyond anything we can replicate on Earth. They exist at the absolute edge of physical law. One step denser and they'd collapse into black holes. If you ever find yourself near one, remember this: don't get close, because physics doesn't negotiate.